Okay, so on the first day of the stats test, the first question tells you that the lifespan of a 60-watt light bulb, 60 is there just as it's just a light bulb. The lifespan of a light bulb produced by a company is normally distributed, so think normal curve, with a mean of 1450. So put your mean of 1450 right down the middle, and the standard deviation of 8.5. If a 60-watt light bulb produced by this company is selected at random, what is the probability that its lifespan will be between 1440 and 1465? So this is an area under the curve probability. So 1440 to 1465. So that's a norm CDF question. The minimum of my interval is 1440. The maximum of my interval is 1465. The mean is 1450. And the standard deviation was 8.5. On your calculator, that comes from second VAERS, so this button right here next to the clear button, and then normal CDF gives you the area under the curve. So there's my numbers: 1440, 1465, 1450, and 8.5. Paste it into your home screen, hit enter, and you get there's an 84% chance, 0.8415 would be what that 4 would get rounded up to. That's option B. Okay. Number 2, a candidate for political office commissioned a poll. His staff received responses from 900 likely voters, and 55% of them, 0.55. So that's the sample proportion that they got, 0.55. Said they would vote for the candidate. The staff then conducted a simulation, and so our simulation results are shown below. In our simulation, we assumed that the 55% was the population. We kind of got to see what our curve would look like after 1,000 simulations. So it looks pretty normal, with 0.55 of course being in the middle, because we told our simulator that 0.55 was was what we were going to assume was the population proportion. So we assumed P matched our sample proportion for the moment. So here, when they want a 95% confidence level and they want the margin of error, the margin of error, like we said, is 2 times a standard deviation. In other words, it's really just coming up with what your standard deviation is. And the best I can say on this one is there's no real calculation you're going to do to come up with a standard deviation, just based on what you guys know about the normal curve. 2 standard deviations away is where 95% of the data. So if we just kind of guesstimated where our 95% interval would be, something maybe like this, where there's a few stragglers outside on either side, but this would be like our 95% of the data is falling between those 2 numbers. So if we estimated what number that would be, this is 0.49, so 49, 50, 51, 52, I would say that's approximately 0.51. And then here, same thing, 58, 59, 60, 61, so this is probably 0.59. So given that 0.55 is our middle, 2 standard deviations away is 0.04. So if that's 2 standard deviations, then 1 standard deviation is probably 0.57, and 2 standard deviations is 0.59. So 2 standard deviations is the 0.04 to get you from 55 to 59. So your margin of error is just 0.04, and it does say closest to, and so 0.04 is closest to 0.03. So that's a game of estimating kind of your 95%, and then that will be 2 standard deviations, and 2 standard deviations is the same as your margin of error. Number 3, we have 2 versions of a standardized test, an April and a May. The stats for the April version show a mean score, so here's April. Show a mean score of 480. And a standard deviation of 24. So I'll just put standard deviation equals 24 in there. The stats for the May version show a mean of 510 and a standard deviation of 20. So it looks like if someone took the May exam, by the way, if the average was much higher, it was probably a slightly easier exam. But at any rate, Joanne took the April version and scored between 510. So she scored between 510 and 540. So that's in here. What is the probability to the nearest 10,000th that a test paper selected at random from this same exam scored in the same interval? So we're just a norm CDF. What are the chances that any of these tests fall in that range? So norm CDF, minimum of 510, maximum of 540, mean of 480 here, and a standard deviation of 24. And we're going to round this to the nearest 10,000. So second VAERS, norm CDF, and I'm just going to input all that. And I get 0.09944011591 to the nearest 10,000th, tenths, hundredths, thousandths, 10,000. So the question is, that's where we're going to cut it off. We got to look at this next number to see if we keep it a 4 or jump it to a 5. And because that's under 5, we're going to keep this a 4. So 0.0994 is to the nearest 10,000th. Okay? To convert to percents, that's approximately a 9.94%, so almost a 10% chance. Okay? Maria took the May version. This is where this one gets a little bit trickier, takes it to the next level. In what interval must Maria score to claim she scored as well as Joanne? Well, she can't just say, well, if I get a 510 to 540, then I scored as well as Joanne, because they took different tests. So we've got to sort of normalize this somehow. So if you look over here and kind of compare what Joanne did relative to her average, okay, the standard deviation on the April version was 24. So we kind of want to figure out how many standard deviations away from 480 this is. It's 30 points higher than the average, but each standard deviation is only 24. So we're almost calculating to a z-score. So our actual score is 510 minus the average 480 divided by the standard deviation of 24. That's a z-score of 510 minus 480 divided by 24 of 1.25. That's your z-score. So we would need to go 1.25 z-scores, or we would need to find the score that's a 1.25 standard deviations above 510. So 510 plus 1.25 of the standard deviations in this case, which are 20, 510 plus 1.25 times 20, so you're going 1.25 standard deviations away. That puts the lower end here at a 535. And this 540 score is 60 above the average, and 60 divided by a 24 standard deviation is going to give you 2.5 as your z-score. So we have to figure out what 2.5 standard deviations above 510 is over here. So 510 plus 2.5 standard deviations of 20, and that gives us a 560. So in April, scoring between a 510 and 540 is equivalent to in May having to score between a 535 and a 560. So in what interval? I would say between a 535 and 560. And we've already shown all of our work. Okay, jumping to number 4, which is an experiment. We've got 72 students randomly divided. Group 1 meets with a tutor. Group 2 is given online access to a program. Okay, and then they're given the same test and they see how they did. So, on average, if you had a tutor, you got an 80. If you were online, you got an 83.4, or 83.8, so closer to an 84. And the standard deviation, meaning the variability, is smaller online. So even the online tutoring kind of resulted in more consistency. These were a little bit more widespread. So calculate the mean difference. That's the difference of the means. Here are your means. Okay. In the final grades, they specifically tell you, as problems will, Group 1 minus Group 2. So that's 80.16 minus 83.8. And that gives us negative 3.64. So explaining the meaning, this means that kids who had a tutor scored on average 3.64 points below those who used online. Okay, and then here we are to our simulation. Use it, and it's 500 times, so we've got to know that there's 500 outputs. Use the simulation to determine if there is a significant difference in the final grades. Okay, our negative 3.64, here's negative 3. So our negative 3.5 is like right there. So anything lower than that, I know we're doing negative 3.64, but we don't have exact numbers, so we'll use that. This bar is about 7 units high, 6 or 7, and this bar is about 3 more people. So let's say this is 6 and this is 3. So out of all 500 simulations, there were 6 here and 3 here, so 9 total. So 9 out of 500 resulted in something that drastic. Okay, and this 9 out of 500, these actually we know for a fact occurred due to coincidental grouping. So 9 out of 500, or as a percentage, that's, as a decimal, it's 0.018, which is 1.8% of simulations resulted in a mean difference less than or equal to negative 3.64 by coincidence. So we can be 100% certain that these 9 simulations occurred where they did, and that was due to coincidence. That is not a very high percentage chance. So that's the percentage chance that we would go with, that this was a mere coincidence. So if there's a 1.8% chance that it's a coincidence, 100% minus 1.8 tells us that there's a 98.2% chance that our observed difference was actually due to the treatment of the tutor versus the online. The difference of negative 3.64 in test grades was due to the treatment. Okay. Describing how a controlled experiment can be created to examine the effect of ingredient X in a toothpaste. So we would essentially want to randomly assign. That'll be a key that I'm looking for. So a group is randomly split and assigned to one of 2 groups. Group 1 uses toothpaste 3 times a day after each meal, and that does not contain ingredient X. Okay, whereas group 2 is going to do the exact same thing. Uses toothpaste 3 times a day after each meal. That does contain ingredient X. In other words, we're keeping as much exactly the same as possible, so there's only one moving part here. That does contain ingredient X. And then after a year, their teeth are checked, for whatever this ingredient was supposed to do. So teeth are checked after 1 year. Okay, to see maybe if those who used ingredient X had less plaque or something of that nature. They don't get into that much specifics about what ingredient X is supposed to be doing, but that's a good controlled experiment because you're controlling and keeping as many variables exactly the same between the two groups, except for the one that you think might be causing something. Okay. On number 6 here, we have 55 students attending the prom. They're randomly selected to, there's way more than 55 students attending the prom, but 55 are chosen to participate in a survey about the music. 60% responded that a DJ would be preferred over a band. So again, we got a sample proportion. So up the sample we took, 60% of them preferred a DJ over a band. Members of the prom committee thought that the vote would have 50 for DJ and 50 for band. So a simulation was run 200 times, each of sample size 55, based on the premise that 60% of the student would prefer a DJ. So again, if you look at your normal curve, because it was based on the 60% premise, 60 is kind of in the middle of your normal curve. The curve doesn't look as perfectly normal as our previous curve did because we only ran this simulation 200 times. The more you run the simulations, the more normal that will look, but you still kind of got that normal flow. Using these results, determine a plausible interval containing the middle 95% of the data. So the middle 95% of the data is, again, 2 standard deviations. We have 2 standard deviations. Our standard deviation was given right up there. So 2 times 0.066 is going to give us 0.132. So we want to be within 0.132 of the middle. So that's going to be 0.60 plus or minus 0.132. So my interval, 0.60 minus 0.132, could be as low as 0.468 or as high as 0.732. In other words, between 46.8% and 73.2% of students likely prefer a DJ. Okay, so that would be our conclusion. Members of the prom committee are concerned that a vote of all students attending the prom may produce a 50-50 split. Explain what statistical evidence supports this concern. Well, it's true. Just because our sample became 0.60, our confidence interval is that the true reality is somewhere between 46.8% and 73.2%. And 50% falls within there. So, since our simulations suggest that the true P, population proportion, is between 0.468 and 0.732, they are correct in thinking it still could be exactly 0.5. Alright, in number 7, an orange juice processing plant receives a truckload of oranges. The quality control team randomly chooses 3 pails of orange, each containing 50 oranges from the truckload. Identify the sample and the population. Okay, so the population is the truck full of oranges. The sample are the 3 pails of 50 oranges. In other words, you could write that 3 pails of 50 oranges, or you could just say 150 oranges that they randomly sampled. State one conclusion that the quality control team could make about the population if 5% of the sample was found to be unsatisfactory. Well, if 5% of the sample was found to be unsatisfactory, they could just generalize that to the entire population, that the entire truckload may have 5% unsatisfactory oranges. That's all. That's one of many. You could run a bunch more statistics and find out more. But if your sample gives you 5%, the entire truckload may have, you could say around 5%, give or take, obviously a little margin of error, but that's good. That's a good enough conclusion.